we need to have a chat. And this chat is about Friedel-Crafts. A chat about Friedel-Crafts? Well, yeah, that's what we're getting ready to do. And we're going to focus on two things of Friedel-Crafts. And the first one is called acylation. Okay, well, what is an acylation? I mean, halogen we've seen before. Nitration we've seen before. Sulfonation was not surprising. And guys, acylation shouldn't be surprising either. What? You mean we've seen this before? And the answer is, yeah, we have. We've talked about the acyl group. Now, we've talked about it very briefly, but we've talked about the acyl group. If I asked you, what is the functional group for carboxylic acid? Well, you would say, oh, well, that's a C double bond OOH. That is a carboxylic acid. Well, that's good. We learned that in Orgo 1. Chemistry 251, start off with acids and bases. This is carboxylic acid, which is a definition of an acid, which is a proton donor, and that hydrogen can go away. Okay, well, this is not really acylation. We're getting closer, though. So the reason I'm doing this is to let you know that we've talked about this kind of group before, and we've really have been using the group all along. We just really haven't discussed it. So this acylation reaction is basically this carbon double bond O. We called this a carbonyl bond. And there were different types of carbonyls. Carboxylic acids, they were a carbonyl, right? And then aldehydes, they were a carbonyl. Ketones, that was a carbonyl. Tons of different carbonyl structures that are out there. But an acyl group in these benzene reactions is basically a carbonyl with something on it, and the other side of the house will get some type of halogen. This is the best template for an acylation reaction, and this is what we traditionally see right there. So that group, whenever we see that group, is going to be termed as an acylation reaction. Now, in particular, we are really focused on this carbon double bond OR. This is what we're really focused on right there, folks. That's the magic piece. That's the piece that makes this thing work. The chlorine is like chlorine any other time. I mean, think about Chemistry 251 when we started talking about substitution and elimination. What did I say? No one wants halogens around. Halogens are very ugly. Boo-hoo-hoo. Away they go home all alone because nobody loves them. Well, the same thing kind of happens here. It's still chlorine. It's still ugly. These compounds are all about face value. They don't care about what's on the inside. It's just about the outside. It's about the attractiveness. And chlorine and bromine and iodine, they really don't have anything going for them. So this is a pretty good leaving group. Oh, well, if this is a pretty good leaving group, and if we can persuade this chlorine to bloop, take those electrons and away it goes, what do we have left? Well, we have left a carbon double bond O with an R that now has a bond that's missing. Oh, well, look, we fit the template now because benzene is going to react with Y positive, which is an electrophile, and right there is my electrophile. And a substitution reaction will happen, and benzene will have a hydrogen that is on that molecule, and like all the other times, there it goes away, and what we have is a carbon double bond O with an R group. Folks, it's as easy as that. But the key here is to get the chlorine off. We have to get that ugly group away. How do we get the ugly group away? Well, we need something to go in to persuade that chlorine to leave. And we do a two-stepper. Two-stepper because two separate steps. In the first step, we add AlCl3. Oh, well, that's pretty similar to FeCl3, right? Well, it is, and it kind of does the same thing. The aluminum and the chlorine have a compound. That chlorine wants and wants and wants and wants and needy. And it takes everything away from aluminum, which makes it slightly positive. And that is very attractive to that chlorine. So there's kind of our first step. The aluminum chloride is going to rip the hydrogen off, and then we're going to add water. Now, I'll talk more about that in just a second, but in our next step, we add water to kind of neutralize everything out of here. Make sure that nothing goes on that doesn't need to go on. You know, we're chaperones. We need to make sure that everything is in place. And aluminum chloride and the water will persuade this reaction to happen. All right, so let me kind of give you an example. This is like a general template again. So let's say that we have benzene, and on this benzene, we have a carbon double bond O with a chlorine on one side, and on the other side, let's say it's a CH3 group, right? It could be as simple as that. No big deal. And then we're going to add aluminum chloride and water. Well, what's going to happen? Well, I don't need to know squat about the mechanisms. I can just kind of predict it. All right, so there's the hydrogen that's on the benzene, and there it goes away. What goes on in its place? Folks, it's whatever's right here. Just ignore the chlorine. The chlorine is a leaving group. It's going to go away, and you just slap on everything else that's there. So carbon double bond O with a CH3 group. It's as simple as that. It's no more difficult than adding a bromo on, or adding a chloro on, or adding a iodo on, or adding an NO2, or adding an SO4H pretty much, right? It's no difference than any of these. But it's the mechanism that might be slightly weird. Okay, well, before I go further, I also need you to know that it doesn't have to be just one C double bond O, meaning that if I throw out something that looks like this also works. So I have a benzene, and here's my C double bond O with the R group right there, right? And I'm going to say that these are the same. Just to keep it simple, I know they don't like to keep it simple, but for us to keep it simple, these two groups are going to be the same. So that way, no matter which side it breaks on, it's going to break. Well, that's an ether, right? No, that's not an ether. It's called an anhydride. Well, wait a minute. I thought ethers were RORs. They are. That definition hasn't changed. And this is a ROR, but it's a special type of ROR. It's a carbonyl with an oxygen with a carbonyl. And whenever we see this formation, Beyonce is going to come around, and that's going to be called an anhydride. All right, so there we go. We can take benzene. We can react it with an acyl chloride. All right, so the acyl chloride is this. Acyl, because of the C double bond O, chloride, because of the Cl group. Or we can react it with an anhydride. And folks, both of these are the same. They both do the same thing. So in this product, I'm going to take my benzene, take the hydrogen, it goes away. And whatever this C double bond O group is, whatever it's hanging out with, that's what's going to come to the party with. Both of those identical. No difference. C double bond O adds on, and it brings with it whatever the R group that we have attached. Now, before we do more examples of these, because these we're going to dive into a little bit more, I want to talk about this catalyst. This catalyst I mentioned was AlCl3, FeCl3, FeBr3, very similar type of concept here. And we're going to bring in this acyl chloride. All right, so let's look at the dynamic here. First off, this C double bond O. We've seen it before. This is not surprising. Oxygen's electronegative. Oxygen wants and wants and wants and wants and wants. And it's going to suck the electrons through the molecule. Well, that's going to expose this carbon a little bit. That exposes that carbon to be slightly positive. This chlorine, well, the chlorine has some negatives around it. That chlorine has negatives around it, so therefore it's slightly negative. And this aluminum, well, it's got 3 chlorines. 1, 2, and 3. And just like the others, free pairs. Just like the others, electronegative. Just like the others, it wants and wants and wants and wants electronegativity. So pull, and we get a partial positive aluminum because of that. So what happens if these two molecules come close? That chlorine looks at the aluminum and says, you're stupid, you're in a relationship, you're letting these people take advantage of you, and that's the exact type of person that I'm looking for. So this chlorine, boom, goes into the aluminum. Well, when it does that, chlorine's going to say, sorry, carbon, sayonara, see you later, and I'm taking all the money. So that chlorine rips the electrons away from that carbon. And what we produce here is a carbon double bond O with a R group. And that leaves behind this positive electrophile piece that then does get eventually added on to the benzene ring, because bigger picture here, we're reacting with benzene. Well, in this dynamic, this is going to form AlCl4 now at this moment, which really carries a negative charge. You know, aluminum with the 3 chlorides, that equals out as far as charges go. Aluminum's a +3, this chlorine's a -1, they cancel each other out, but now I add on another chlorine, which means I add on another negative charge from the ion chart, which means that this is AlCl4-. So the issue here is, why is water needed? Well, here's why. When this group gets added on to a benzene ring, so get rid of that positive, that now has a bond, and that bond is going to be to a benzene. So there we go. When this happens, we're going to see some free dots appear near oxygen, just like before, right? And we also see this carbon double bond O have some slight polarity that's associated with it. So slightly negative and slightly positive. That's not surprising. And this AlCl4 that was generated in the reaction, it can, and then it comes into this molecule and it says, there's nothing here for me. So, there it goes away. It doesn't really bother with that molecule. The reason there's nothing there for it is AlCl4 is negative, and it's going to come into the benzene ring, which is negative spreaded throughout the ring. And then it's going to look at the carbonyl bond, and it's going to see that negative oxygen, and it really can't get in anywhere at this point. to kind of do anything at all. So the AlCl4 is not what we're worried with. What we're worried with is the AlCl3. Think about it. This was step one. There could be remaining AlCl3 that's there that didn't get used up. So in the reaction, if you think of yourself doing it in the lab, you're adding and adding and adding, and a reaction goes forward, and you start making this product. This is the product you're making right there. As you're making this product, you cannot assume that all of the AlCl3 has been used up. There still could be some left behind. And the problem with this is this AlCl3 is going to behave just like it did before. These chlorines pull the electrons away from the aluminum, making this slightly positive. And ding ding, look here. There's a carbonyl, there's an oxygen, there's free pairs of electrons. What do you think's going to happen? Well, this negative area is going to be attracted to that positive aluminum, and we're going to see an aluminum that brings those 3 carbons to the party, right? I mean, that's what's going on here with this structure. Now, the issue here is that if this happens, this messes my product up. That's not what I want. I do not want that aluminum chloride to basically take over that oxygen and stick to it like glue. I mean, this is like taking your guy best friend or your girl best friend to the bar, and everybody thinks that you're dating when you're just really best friends. We don't want that kind of dynamic here, especially if you're looking for a relationship. So you want to make sure that you stay apart. You want to make sure that this bond doesn't get too tight. And that is the purpose of the water. So what happens is that the water will come in, and the water will take this piece and get rid of the aluminum chloride. Poof! Away it goes. So when it does that, what we end up with is the water and that aluminum chloride basically ending up to be aluminum hydroxide, and it generates a little bit of acid for us, hydrochloric acid. So it completely decomposes that big, meddlesome, nasty friend that comes to the bar with you that everybody thinks that you're dating when you're actually just friends. Completely decomposes that relationship around. So that way we get the product that we're after. So this is the mechanism of the acylation reaction. Okay. So it looks like the only thing that goes on here is that I take my benzene, there we are, and I bring in some type of acyl halide, carbon double bond O, with maybe a chlorine. A lot of times they'll write the chlorine over to the right-hand side, so I'm going to do that so I don't mess you up. And then maybe this carbon, it's got like an isopropyl group on it. I mean, I don't know, right? We can try it. So can I just simply take this benzene, get rid of the hydrogen, this chlorine leaves because it's a good leaving group. That's where the carbon double bond O comes into play. And then off of this carbon, I'm going to get the isopropyl group. In theory, that is what should happen. It's as simple as that. It's another slap on the benzene. That's really it. We add the halogen on. We add the NO2 on. We add the sulfonate on. And now we add the acyl on. Nothing more. That's all that we've got to do. Additionally, also keep in mind, The anhydrides are also fair game. That's fairly new to us at this point. So let's do CH3 there and a CH3 here. If I react that with benzene, what I end up getting is my benzene with a hydrogen. And these are the same. They're pretty good about it. They'll keep them the same. If not, you'll just get a mixed product. Sometimes it will be this acyl group to the left. Sometimes it will be that acyl group to the right. You'll get a mix. Alphabet soup. All right. Well, that carbon, double bond O, and what does it bring? It brings that CH3 group. The R group is what it brings to the party. Folks, that's it of the acylation. Very straightforward. Very simplistic compared to some of the other reactions that we've been doing, right? Especially in Orgo 1. Doesn't seem too bad. And to be quite honest, the majority of the benzene reactions are that way as well. They're not bad at all. It's just a matter of a very simplistic, basic foundation that we can add our starting group on. Oh. Starting group. Wait a minute. This bromo and the iodo and the chloros and the nitros and the sulfonates and all of these others are just starting pieces? Yeah. Unfortunately, that's the way it is. Inorganic. You know that. You know me. They're going to build on top of each other. So we've got one more reaction that we need to talk about. And this reaction is going to be called alkylation. Friedel-Crafts alkylation. How is it going to be different than acylation? Well, it's an alkyl group, not an acyl group. Well, go figure. So that's what we'll talk about in the next video. We'll look at our final reaction, and that final reaction formally with benzene is going to be the Friedel-Crafts alkylation. And that's where we'll pick up when you come back.